Welcome to the first episode of Digital Dialogues, the Apex Waves podcast, where we dive into the world of technology, innovation, and engineering solutions. We're so excited to have you here for this journey. Let's dive into our first topic. Imagine trying to recreate your grandmother's secret recipe when all you have is the final dish. No ingredients list, no instructions, nothing. That's exactly what a team of engineers faced when they had to replicate a critical aircraft radar component with zero documentation, or planes could literally fall from the sky.
So what makes this particular challenge so fascinating? We're talking about a component that quite literally keeps aircraft safe. These engineers basically had to become technological detectives, working against the clock to solve this mystery.
And we're not talking about some minor component here. This beam steering controller was absolutely crucial for aircraft safety. Without it, thousands of radar elements couldn't focus into a single beam, essentially leaving aircraft flying blind.
So what made this particular challenge so difficult?
Well, they were dealing with completely obsolete technology, 9-volt DC CMOS systems and PROM-based state machines. It's like trying to rebuild a 1980s computer with modern parts, but you have to make it work exactly the same way.
Kind of like trying to repair a vintage car when the manufacturer no longer exists and you don't have any maintenance manuals?
Exactly. And the stakes were so much higher. These engineers had to figure out how to capture and decode thousands of electronic signals without even knowing what they meant. They basically created a high-tech surveillance system to eavesdrop on computer conversations.
How did they even begin to approach this? I mean, where do you even start with a challenge like that?
Here's where it gets really clever. Instead of trying to understand how the original device worked, they essentially created a high-tech surveillance operation using LabVIEW FPGA technology. They built this custom cable that could monitor every single signal going in and out of the controller. Think of it like having a universal translator for computer signals. Within just hours, they had created an emulator that could capture and replay these complex commands.
So rather than reverse engineering the whole thing, they just needed to copy what it did?
Exactly. They didn't even need to understand what all the signals meant at first. They just needed to record the patterns and responses. Think of it like creating a perfect musical cover version. You don't need to know what inspired the original artist, you just need to reproduce the sound perfectly. They automated the entire process to test every possible command combination and record the outputs.
So they were essentially creating a massive database of cause and effect, right? If signal A goes in, signal B comes out? That must have generated an enormous amount of data to process.
Oh, you better believe it. We're talking about thousands of different command combinations. But here's the brilliant part. They created this system that could automatically cycle through every possible input and record exactly what the original controller did in response. They automated the whole process using these specialized PXI modules, industrial-strength computer components that could systematically try every possible combination of commands and record what happened.
Well, that's fascinating, but surely there were some complications along the way.
The biggest challenge was actually dealing with the voltage differences. Modern equipment operates at much lower voltages than the original 9-volt system.
How did they solve that particular problem?
Through some seriously impressive detective work, they managed to track down the exact same type of output driver chips used in the original controller. Then they designed a custom circuit card that could translate between the old and new voltage levels.
You know, what's really impressive? They managed to do all of this in just a few weeks.
Right. And that's practically unheard of in the engineering world. The key was their approach. Instead of getting bogged down in understanding the underlying logic, they focused solely on recreating the behavior.
You know what strikes me about this whole story?
What's that?
It really shows how engineering isn't just about creating new things. Sometimes it's about preserving and adapting what already works. That's exactly the kind of innovative thinking we need more of in engineering. Using new technology to bridge gaps with legacy systems.
That's such an important point. In aerospace especially, we can't just replace everything every time technology advances. Sometimes the most innovative solution is finding ways to keep critical legacy systems running.
Looking ahead, what do you think this means for similar challenges in the future?
Well, I think this case really demonstrates the power of modern diagnostic tools and creative problem solving. As more legacy systems age out, we're going to need more solutions like this. ways to bridge the gap between old and new technology without compromising safety or functionality.
So, this could potentially change how we approach maintaining and upgrading other legacy systems?
Absolutely right. Think about all the aging infrastructure and industrial systems out there. This approach could revolutionize how we handle technological transitions. Instead of replacing entire systems, we could create modern equivalents that perfectly replicate the behavior of older components. These engineers essentially created a perfect mimic without ever fully understanding the original device's internal logic.
That's a really important insight for the future of engineering. That's going to save an enormous amount of time and resources in the long run.
And here's what I find most satisfying about this whole story. Somewhere out there, there's an aircraft flying with this replacement system, and nobody can tell the difference. It's doing its job so perfectly that it's completely invisible to the end users.
That really is the ultimate measure of success in engineering, when your solution works so seamlessly that nobody even knows it's there.
Looking ahead, I think this case study is going to become a blueprint for how we handle similar challenges in the future. It's about working smarter, not harder, and sometimes that means thinking completely outside the box. And you know what? It's not just about engineering. This approach of breaking down seemingly impossible problems into manageable pieces is something we can all learn from. Sometimes the best solution isn't understanding everything, but finding creative ways to make things work.
And that's a wrap on today's topic. Thank you so much for tuning into Digital Dialogues, where we keep the conversation flowing. Don't forget to follow us on social media at Apex Waves for updates, insights, and more.
Be sure to follow us here too so you can tune in for the next episode.
Remember, at Apex Waves, we specialize in all things obsolete, helping you keep the legacy alive.
Until our next deep dive, we'll catch you in the next conversation.